Good afternoon, everyone. In the beginning of the class, let us look at new announcements. Okay, the first new announcement is April 18th, 2022. Class videos uploaded. Hello everyone, I have uploaded the class videos of April 18th, 2022 to YouTube. Their URLs are this, and this. Okay, best regards, Wei Zhen. Okay, the next new announcement is Homework 2 problem has been uploaded. Hello everyone, I have uploaded the problem of Homework 2 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, homework, Homework 2 problem 20220420.pdf. Best regards, Wei Zhen. Okay, the next new announcement is this month is online teaching. Dear everyone, this month, April 1st to 30th, 2022 is online teaching. Best regards, Wei Zhen. Okay, the next new announcement is the slides of Chapter 3 has been updated, version 20220420. Hello everyone, I have uploaded the latest version of the slides of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multi-input, multiple output techniques for wireless communications. Course content, slides, Chapter 3 slides 20220420.pptx. Best regards, Wei Zhen. Okay, the next new announcement is the handout of Chapter 3 has been updated, version 20220420. Hello everyone, I have uploaded the latest version of the handout of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website, multiple input, multiple output techniques for wireless communications. Course content, handouts, Chapter 3 handout 20220420.pdf. Best regards, Wei Zhen. Okay, next let us look at Homework 2 problem. Okay, Homework 2 problem. Okay, this is Homework 2. Today is the date of assignment, April 20, 2022. And the deadline is April 27th, 2022. So there is only one problem. Okay, problem 1, coin flips. A fair coin is flipped until the first head occurs. Let X denote the number of flips required. A. Find the entropy H of x in bits. The following expressions may be useful. Okay. Summation n is equal to 0 to infinity. R to the power of n is equal to 1 over 1 minus r. And summation n is equal to 0 to infinity. N times r to the power of n is equal to r over 1 minus r squared. Okay, this is equation 1. And A contains 50 points. B. A random variable x is drawn according to this distribution. Find an efficient sequence of yes-no questions of the form: is x contained in the set S? Compare h of x to the expected number of questions required to determine x. 50 points. Okay, notice 1. I encourage you to discuss with other students. However, if you copy someone else's homework solution, or you borrow your homework solution to someone else for him or her to copy, your score will be 0. 2. If you hand in your homework after the deadline, your score will be 0. Three, please email your homework solution to Professor Wei-Jen Liu. His email address is comwcliu@ccu.edu.tw. Okay, that's all. Okay, next let us look at the progress of the last class. In the last class, we have taught to Chapter 3 slides, page 4, line 1, unfinished. Okay, please open Chapter 3. Okay, here. And turn to page 4. Okay. So under the CSIR only assumption, okay, what is CSIR only? Okay, the CSIR only means that only the receiver knows the channel state information, but the transmitter does not know the channel state information. Then what is channel state information? Okay, the channel state information is the channel matrix H. The transmitter does not have knowledge about the communications channel, so there is no basis for transmitting signals in any sort of preferential. Okay, what is the meaning of preferential? Let us see the handout. Okay. Okay, page 5, problem 1. What is preferential? Okay, let me enlarge it. Solution: used to say that something you are given that is better than what other people receive. Oh, sorry, it should be page 4. Okay, I will correct the handout. Okay, preferential weigh on different antennas. This fact has two implications. Okay, what is implications? Okay, let us go to the handout. Okay, here. Okay, problem 2. What is implication? Solution. An occasion when you seem to suggest something without saying it directly. Okay, it is implication. Okay, first, there is no reason to transmit more energy on one antenna than another. Thus, the average signal power should be the same on each transmit antenna. 2. There is no reason to introduce correlation or dependence between antennas. In summary, under the CSIR only assumption, transmitted signals on each of the NT transmit antennas are equal power, independent, and uncorrelated. Of course, if two random variables are independent, then they are also uncorrelated. Okay, to understand the implications of these assumptions, we start with the following version of the MIMO system equation. R is equal to the square root of rho times H prime times S plus Z. Okay, where R is the NR by 1 received signal vector. H prime is the NR by NT normalized channel matrix. Okay, I have told you, when you see a vector or a matrix, you should know the dimension of them. Okay, and what is the meaning of normalized? Okay, we will see the meaning of normalized later. S is the NT by 1 transmit signal vector. Z is the NR by 1 noise signal vector. And rho is the signal to noise power ratio at the receiver. Okay, please note that it is the SNR at the receiver. The SNR as the transmitter and the SNR as the receiver is not the same. Okay, because the difference is the transmitted signal will times this term. Okay, the square root of rho times H prime. Okay, so the SNR at the transmitter and the receiver are not the same. Comparison of this equation with equation 2.15. Okay, let us go to equation 2.15. Okay, 2.15. Okay, in equation 2.15, we can see that R. Okay, let me enlarge it. R is equal to H times S plus Z. Okay, let us go back to chapter 3. Okay. Okay, shows that they differ by the coefficient square root of rho. That is, the product square root of rho times H prime is equivalent to the physical channel matrix in equation 2.15. Okay, that is, okay, in equation 3.1, the term square root of rho times h prime is equal to h in equation 2.15. Okay, let us go back to chapter 3. Okay. Appendix A. Okay, please note that I do not put Appendix A in these slides. Okay, because if we go through Appendix A, okay, it will spend us too much time. Okay, Appendix A shows that when the system equation is expressed in the form shown in equation 3.1. Okay, let us see equation 3.1. Okay, it's this equation. The following normalizations are implied. Okay. First, the expectation of the square of the absolute value of hij prime is equal to 1. Okay, where hij prime is the element in the ith row and the jth column of the matrix H prime. Okay, this is for random H prime. And the square of the Frobenius norm of H prime is equal to nr times nt. This is for fixed H prime. Okay, and the expectation of the square of the absolute value of zi, okay, where zi is the ith element of the vector z. And what is vector z? Okay, z is the nr/1 noise signal vector. And we define this term as sigma square, and it is equal to 1. Okay, finally, the expectation of square of the absolute value of Si, where Si is the ith element of vector S. Okay, S is the nt/1 transmit signal vector, and which is defined as sigma s squared, and it is equal to 1 over nt, where sigma s squared, okay, here sigma s squared denotes the signal variance applied to each transmit antenna. The form of the system equation shown in equation 3.1. Okay, let us go to equation 3.1. Okay, this equation, r is equal to the square root of rho times h prime times s plus z. Okay, is commonly used in MIMO literature. It has the advantage that it includes rho explicitly. Okay, what is the meaning of this word explicitly? Let us see the handout. Okay, page 10, problem 1. What is explicitly? Okay. The solution is in a way that is clear and exact. Okay, which allows the user to make theoretical capacity predictions as a function of the signal to noise ratio. For this reason, the form of the system equation in 3.1. Okay, let us see equation 3.1 again. Okay, this equation. Okay, r is equal to the square root of rho times h prime times s plus z. is used throughout a large portion of this course. Implications 1 and 2. Okay, what are implications 1 and 2? Okay, it is these two implications on page 5. Okay, above imply that the signal covariance matrix has the following form. RSS is defined as the expectation of S times S Hermitian and is equal to sigma S squared times INT. Okay, it means that the power of each symbol on each antenna is equal to sigma S squared. And the signals on different antennas or on different transmit antennas are uncorrelated because their covariance is equal to 0. Plugging this expression for RSS into equation 2.35. Okay, let us go to equation 2.35. Okay, chapter 2, equation 2.35. Okay, this equation. Okay, let us review this equation. C complex, that is the capacity of complex signals, is equal to log 2 of the determinant of I, okay, where I is an identity matrix, plus 1 over sigma square, where sigma square is the noise variance, times H is the channel matrix, times RSS, okay, where RSS is the covariance matrix of the transmitted signal, and times H Hermitian, okay, and the unit is bits per channel use. Okay, let us go back to chapter 3. Okay, so into equation 2.35 results in the following expression for the capacity. Okay, we know that the capacity is equal to log 2 of the determinant of INR. So it means that it is an NR by NR identity matrix, plus 1 over sigma square times H times RSS times H Hermitian. Okay, because RSS is equal to sigma S squared times INT, so we can put sigma S squared here, and INT here times H is also equal to H. So RSS will disappear, and the remaining term is H times H Hermitian, where the second equality follows from the two implications listed above for CSIR only. That is, equal power and uncorrelated signals from different antennas. Okay, or you can say this follows from equation 3.6. If we now substitute H, which is defined as the square root of rho times H prime, into equation 3.7. Okay, let us go to equation 3.7. Okay, is this equation. And use equation 3.4. Okay, let us go to equation 3.4. Okay, In equation 3.4, it is written the expectation of the square. Okay, it is 25 minutes. Let us take a break.